Check one. Check 1, 2, 3. Uh, Hello, everybody. Is it loud and clear? Can you all hear me clearly? Yeah, put in the chat. Hello, everybody. Can you all hear me clearly? Is it loud and clear? You can indicate that in the chat. You can indicate that in the chat now. Good evening, everybody. Can you all hear? Is it loud and clear? You can put in the chat. Huh? Is it loud and clear? If one person can put in the chat, it's good. Please, one person. Can hear? Okay, let's start. Right. Good evening, everybody. Uh, as promised, today we'll be discussing the essay part for the questions that we discussed unit test 4. Yeah. So take the essay part, MCQ part. I think we have done. Essay part. Let's start. Question number 1. Question number 1. A light inextensible string attached to a vertical wall. At one end, the string is kept horizontal by applying a horizontal force F on the other end. Find the following. So it's about a horizontal string. Huh? The first part, horizontal string. Keyword there is what? Light inextensible string. Light. I'm applying a force F. So they're asking you tension at points A, B, C, D. A, B, C, D, E. There you go. Everywhere the tension will be the same. Tension at A equals, tension at B equals, tension at C equals, tension at D equals, tension at E, everything is equal to how much? No change. Everywhere tension same. Okay. Right. Total force on the string at points A, B, C, D, E. Total force. Now if you take this point here, equal opposite forces everywhere you can see. What can you say? The force there, this force and that force will cancel off. Total force at each and every point is how much? 0 newtons. Part C. Tension at A, B, C, D if it is a heavy rope. Now heavy rope also, let's say it's a heavy rope, we'll draw it. Heavy rope. I'm applying a force F. They are saying this is horizontal. Now we have done sonometer. Horizontal force applied means tension everywhere remains the same. No change. The tension is the same. So technically tension remains the same. Tension at A equals, tension at B equals, tension at C equals, tension at D equals, tension at E equals. Same force F. No change. So just like in strings. Horizontal force, everywhere the tension is the same. Right? A sonometer problem, that's how we solve. Right. This is horizontal. Then comes to the vertical part. Roman 2. When the string is kept in the vertical position, the vertical force is applied to the lower end. The vertical force is applied to the lower end. Above string. Light inextensible string. Light inextensible string, vertical. And I'm applying a force F. So everywhere you see A, B, C, D, and also E. Light inextensible string. Tension at A equals, tension at B equals, tension at C equal, tension at D equal, tension at E equals what? F. Light string, force is always what? Same. Force is always the same. What's the total force? So total force here, if you just mark it, total force at each and every point, total force at each and every point will be 0 Newton. So above rope, the rope told in the question is light. Then comes part C. Tension of the string at points A, B, C, D, E if the mass per length is simple M. Assume that the distances A, B, B, C, C, D, D, E are equal. But now this part is different. Now you have a heavy rope. Now you have a heavy rope. You're applying F here. So here A, B, C, D, E. So here now, first question, tension at A. Tension at A means we can make an imaginary cut at A. Tension at B means make an imaginary cut at B. Tension at C means make an imaginary cut at C. Tension at D means imaginary cut at D. Tension at E means if you want, you can cut it there. So if you take this, here you have tension at A. Tension at A. Total weight of each of these sections. A, B, B, C, C, D, D, E. Even this part. All these are equal lengths. Right. So mass per length, simple M. Simple M into 1, 2, 3, 4, 4L G. Simple M into 4L G. So mass per length is already given. No? Yeah. Mass per length is already given. And don't forget, here there is a force F. Mass per length is given. Here you have a force F. Now you must calculate this. You must calculate this. From here you can simplify and write very simply. Upward forces, balances, downward forces. Tension at A is equal to 4mLg plus F. F is always there. Then the tension at E. Make an imaginary cut at B. Tension at B here, dB. What is your total weight? 1, 2, 3. Simple M into 3Lg. Don't forget F is also there. Sum of forces acting upwards balances sum of forces acting downwards. Simplify it carefully. Tension at B is equal to, weight here is 3mLg plus the force. Plus the force. Tension at C. Tension at C. Tension at C. Here F. Simplify this carefully. Tension at C means only two lengths are there. 2Lg. Sum of forces in the upward direction balances sum of forces in the downward direction. Tension at C is 2mLg plus F. 2mLg plus F. Right? Then tension at D. Tension at D. Make a small imaginary cut. Here tension at D. Here F is there. Here you can take mLg. Sum of forces in the upward direction balances sum of forces downward. Tension at D is mlg plus force. What about tension at E? E, there is no weight underneath it. So tension at E will be equal to directly what to F. Okay. Tension at E is equal to F. Right? There you go. So there you go. Part A done and finished. Part B. Part B. The tension force and normal reaction force acting on object is shown. So here you go. Weight of the object is W. Normal reaction R. Tension here T. Now they are given you how the tension changes. They are given you how the tension changes with time. Tension changes with time. Here is W over 2. W over 2. Right. Write the relationship between TR and W. So easily we can write sum of forces in the upward direction balances sum of forces in the downward direction. T plus R equals W. T plus R equals W. Draw the variation of R with tension. Draw the variation of R with tension. So when tension changes, how will R change? You can see the graph. Graph is of the form y is equal to minus x plus c. So tension was in Newton. Normal reaction was in Newton. So we can plot a graph here. Tension is 0, R is W, tension is maximum. Tension maximum W over 2. Normal reaction 0, tension equal W. So this graph continues technical. Like this. Please name it. This is W. This here also will be W. Right. Tensile force varies with time as shown. Draw the variation of R with time. Draw the variation of R with time. So this is Roman number 2. Roman number 3, how tension or reaction forces vary with time. Reaction forces varies with time. Right. You can solve it very simple. I'll take this 0, I'll take this maximum T. Let's say the symmetrical somewhere like T over 2. Symmetrical. So when time is equal to 0, tension is also equal to 0. If tension equals 0, normal reaction is W. Then when time is equal to capital T over 2, half a periodic time, let's say T dash easier. Otherwise you might confuse it with tension. So W over 2 means tension will be W divided by 2 maximum. Substitute W over 2 here. Normal reaction is W over 2. Next, when time is equal to T dash, again tension 0 are equal W. So here I can easily see it that the variation is like this. W over 2 again W. So it's a graph like that. You can draw this Newton and take the rest second. That's how your graph is. Simple variations. Next one, part C. Part C. Here there is a mass. Here there is a mass. We are applying a tension T1. We are applying a tension T1. This is connected by a mass to another object here. Another object there. M1 is 2 kilogram. M1 is 2 kilogram means 20 Newton. M2 is 3 kilogram means 30 Newton. Simplify it. You can mark the tension like this. Like two light strings. Both are light. That's the question. Find the tensions T1 and T2 when the mass is at rest. When the mass is at rest. So part A. Roman 1 part A. F equal ma vertically on 2 kilogram. T1 minus 20 minus T2 mass into no acceleration. T1 minus T2 is 20. Equation 1. T1 minus T2 is 20. Equation number 1. Then you apply F equal ma. Apply on 3 kilogram. So very direct. So here T2 minus 30. 3 times no acceleration. So there is no acceleration. So T2 equals how much? 30 Newton. Substitute there. T1 minus 30 equals 20. T1 equals how much? 50 Newton. T1 equals 50 Newton. Part B. Part B. When they are moving with a uniform velocity, remember uniform velocity means acceleration 0. So tension will be the same. So constant velocity means acceleration is 0. The same answers. T1 is 50 Newton. T2 is 30 Newton. There you go. Part C. When they are moving upwards with the uniform acceleration. Right. So here when they are moving upwards, F equal ma upwards. Apply for 3 kilogram. Apply for 3 kilogram. 3 kilogram you have T2 minus 30. Mass into acceleration. They are given you acceleration here 2. Acceleration here 2. T2 is equal to 36 Newton. If T2 is equal to 36, apply here. F equal ma vertically. 2 kilogram object. T1 minus 20 minus T2 equals mass into acceleration. Mass into acceleration is 2. That's also acting upwards. This is going upwards when these also going upwards. T1 minus 20 minus 36 equal 4. 56 plus 4, therefore T1 is 60 Newton. T1 is 60 Newtons. Okay. T1 60 Newtons. Right. Then moving downwards with the acceleration. Part D. F equal ma downwards. F equal ma downwards. Apply on 2 kilogram. T2 plus 20 minus T1 is mass into acceleration 2. Simplify this. T2 minus T1. T2 minus T1. Downward acceleration. There you go. T2 minus T1 is minus 60. Apply F equal ma in the downward direction on 3 kilogram. 30 minus T2 mass into acceleration 2. T2 is equal to 24 Newton. T2 24 means 24 minus T1 equal minus 60. T1 equal 40 Newtons. Therefore, you can see T2, T1 separately found. 24 Newton, 40 Newton, done. Okay, right. Then Roman 2. Then Roman 2. If the maximum tension that the string can withstand is 100 Newton, find the maximum upward acceleration that the mass can have and the tension in each of the strings. Right. So remember, the greatest force is acting on this rope. Greatest force. This weight is there. This weight is also there. So greatest possible tension can happen in the upper rope, not the middle rope. Okay. Right there, small sentence. Roman number 2. The greatest possible force occurs on the upper rope. The greatest possible force occurs on the upper rope. So here you can write. Here you can write. Maximum is going to be 10. Here it's going to be 20 Newton. Here it's going to be 30 Newton. Here T2. Right. If the maximum tension is 100, find the maximum upward acceleration and the tensions in the string at once. Now you can apply F equal ma upwards for the system. What do you mean by system? System means all this. If I take the full system, tension will cancel off. So apply 100 minus 20 minus 30. Total mass is 5 into acceleration. 100 minus 50, 5 times A. 50 divided by 5, there you go, acceleration. That is going to be 10 ms minus 2. 10 ms minus 2. Find the tension of the string at this instant. Therefore, T1 is equal to 100 Newton. Carefully look at T2. If you apply F equal ma on 3 kilogram mass, T2 minus 30 mass into acceleration is 10. Therefore, T2 is equal to how much? 60 newtons. T2 equals 60 newtons. Okay. Part C done. Part D. Part C done. Part D. A length L cross-sectional area A is pulled along a smooth horizontal surface with a force F. Density of the rope is rho. So here you go, heavy rope. Heavy rope pulled with a force F. Cross-sectional area is going to be A. Length of the rope is going to be what? L. Carefully work. Write an expression for the total mass. So we can say total mass here. Total mass is cross-sectional area into length is volume times density. AL rho. What's the acceleration of the string? Apply F equal ma in the forward direction. Force mass is AL rho into A. Acceleration is force AL rho. Force times AL rho. Write an expression for the tension at a distance x from the rod. Distance x from the rod. Make a small imaginary cut. Make a small imaginary cut. So it's 2 parts. Here L minus x is pulled by tension. Here x is also pulled by tension in the opposite direction. Here force F. Separately you have the mass here. M1. Separately you have mass here M2. Right. What are they asking you? Tension. No? So what's your mass per length? Roman 3. Mass per length. AL rho divided by L. That is A rho. Mass per length, simple M. So what is the mass M1 here? M1 is mass per length into length. A rho X. A rho X. Simple M1. They want you to find the tension. Remember the acceleration here and the acceleration in each part here and here both are same. Same acceleration. So I'll do it here and finish it off. I have some space on top. No. I'll do it somewhere here and finish it off. Apply F equal ma forward. F minus tension, mass into acceleration. Mass is mass per length m1. A rho x times acceleration A. There you go. Tension equal F minus A rho x times A. Acceleration is what? F divided by A L rho. Simplify this. A rho cancel off. T1 take F out. 1 minus x over L. There you go. There you go. Easily we can find. Easily we can find. Easily we can find. It's not over yet. Draw the variation of force with distance. So the force is here, no? Tension force. So I can say tension force is equal to F times 1 minus x over L minus F over L times x plus F. Graph is of the form y equal minus mx plus c. So tension with distance, here you go. Y-intercept is going to be F. Y-intercept is going to be F. When the length is L, tension is going to be 0. You can name the axis as n and this is in whatever unit, centimeters or meters, whatever you want. Okay. Right. So there you go. Question number 1, which consists of 4 parts, done and finished. Done and finished. Here you go. Question number 2. Here you go. Question number 2. Figure shows 3 forces acting on a box of mass 0.75 kilogram variation. Here you go. The box is there. Box is there. Here, external force is applied. External force is applied. Air resistance is there. Frictional force is there. Air resistance is there. Frictional force is there. Right? 0.75 kg. Right. They are given you the force. Each force, how it varies. F1 varying with time is constant. F1 is going to be 4.5 Newton. F2 is going to be 1.5 Newton. F2 is going to be 1.5 Newton. F2 is going to be 1.5 Newton. And F3 is going to be, F0 is going to be, sorry. F0 is going to be, with velocity F0, keeps on increasing. There you go. Right. Now carefully answer these questions. Answer the following questions using the graphs. What is the resultant force acting on the object when the initial velocity is 0? So velocity 0 means air resistance 0. First part. Rope 1 part A. V0 means F0 is equal to 0. F0 is equal to 0 means what's the resultant force? This is 4.5. Already they are given now 4.5 Newton. This is already 1.5. So resultant force is going to be 3 Newtons. Resultant force is going to be 4.5 minus 1.5. Altogether how much? 3 Newtons. 4.5 minus 1.5, 3 Newtons. What's the initial acceleration of the box? So I can answer this part B here. Apply F equal ma in the forward direction. Resultant force is 3 Newton. What is the mass of the object? Mass of the object is 0.75. 0.75 is 304 kilogram. A is equal to 4 ms minus 2. Remember 0.75 kilogram means 304 kilogram. Don't forget. 304 kilograms. Right. 304 kilograms. What's the next one? Next one. Right. What is the maximum acceleration of the box? You all tell me. Maximum acceleration occurs when there is a maximum resultant force. Now with time the velocity will increase, more force there, resultant force will reduce. So maximum acceleration technically is here. A maximum is actually 4 ms minus 2. Right there, small sentence. Maximum acceleration will occur. Maximum acceleration will occur. Maximum acceleration will occur when the resultant force is maximum. When the resultant force is maximum. When the resultant force is maximum. The resultant force will be maximum. The resultant force will be maximum. The resultant force will be maximum. Initially when t equal naught. Initially when t equal naught. Initially when t equal naught. So here you go. 4 ms minus 2. Right. Roman number 2. Roman number 2. What is the magnitude of f naught when the velocity of the box is maximum? How do you find the maximum velocity? When Roman 2, V max occurs, acceleration is going to be how much? 0. So when maximum velocity occurs, acceleration will be 0. So how will you find this? Now if you look at this carefully, they are given you forward force 4.9 newtons, 4.5. Here it's going to be 1.5 Newton. So to balance this, F naught will be how much? F naught will be how much? 3 Newtons, right? 3 Newtons means acceleration here is going to be 0. Velocity is going to be maximum. Now go to the graph. Go to the graph. Force is 3 Newton. Corresponding velocity how much? Corresponding velocity is 15 meter per second. So corresponding velocity from the graph we can find. From the graph we can find V max is equal to 15 meters per second. V max equals 15 meters per second. Right. Then what? So part A done. This is part B. Calculate the value for K. Right. Part C. F naught equals KV squared. No. F naught is 3 newtons. K times V squared is 15 squared. K equals 3 over 225. That's 1 over 75. Newton. Force is Newton. M minus 2 is positive 2. That means S squared M minus 2. You must put the unit, otherwise can't. Draw the corresponding velocity time graph for the motion. So how will I draw the VT graph? Simple, no? Why? Maximum velocity is reached. Acceleration will reduce and reach maximum velocity. There you go. This is your graph. Some of you all don't know. Acceleration is maximum in the beginning. Acceleration maximum, now acceleration 0. So VT graph, gradient is maximum, gradient is 0. So it's a curve like this. Basic work. There you go. Right? Part B. Part B. Part B. A mass 2 kg is kept on the mass 4 kg. Mass 2 kg is kept on a mass 4 kg. Mass 2 kg is kept on a mass 4 kg. So here it's going to be 20 newtons. Normal reaction R1, equal opposite normal reaction. Here you're going to be 40 newtons. Here you'll have normal reaction R2. What are they saying? Kept on a frictionless horizontal surface. And a force 3 newtons is applied here. 3 newtons applied. Right. What are they asking? If there is no friction between M1 and M2, no friction here, draw and label the forces. Find the acceleration of the two masses. So you're finding the acceleration of the two masses. So this is very simple and direct. Huh? Simple and direct. This force is acting on this mass. No? There is no force acting there. So if I write this is M1, this is M2. So if I write F equal MA on M1, no force, whatever the mass, acceleration guaranteed will be 0. Here no friction, huh? They have told this part. This is B Roman 1. B Roman 1. Part A done, this part B. Then I apply F equal MA on M2. 3 Newton is the applied force, 4 times acceleration, A2. Acceleration is 0.75 ms minus 2. Acceleration 0.75 ms minus 2. Right. Roman 2. Roman 2. If there was sufficient friction, enough friction between the two masses, so they don't slip, do not slip. No slip means very simple, moves together. Moves together. No slip means moves together. So draw and label the forces. Well, we'll draw again. Huh? You can't draw on the earlier diagram, you must draw again. Some of you all, because you're lazy, you won't draw again. No, you have to draw again. That's part of the working. 20 newtons here, normal reaction here. Equal opposite normal reaction there. 40 newtons here. Equal opposite normal reaction there. Here smooth. Here you're applying a force. F. If there was sufficient friction means here, friction will act in that direction, FR. Equal opposite friction on that in the forward direction. No slip means what? No slip means both of them will go together. Both of them will go together. So here you will work it out. Very simple. If both of them are going together, force applied how much? 3 newtons. So I can apply for the system F equal MA. Part B, part A done. F equal MA for the system, let me apply. Forward. Applied force is 3, total mass. System means FR cancel off. Here 6 times A. Acceleration is 0.5 ms minus 2. Acceleration 0.5 ms minus 2. So both the masses will have the same acceleration. Both are going together, same acceleration. Next, find the magnitude of the frictional force. Let me apply F equal MA on 2 kilogram mass. Friction equal 2 times acceleration 0.5. Friction force is going to be 1 Newton. Friction force is going to be 1 Newton. There you go. Roman 2 part A, B, C. So these are very basic, simple work. Nothing to think much. Very simple. Directly apply, you have your answer. No slip means they move together. That means they are having the same acceleration. This and that both will have the same acceleration. Right. Part C. Part C. Have a look. Two boxes mass 2 kilogram and 4 kilogram are kept on a smooth horizontal table as shown. So 2 kilogram and 4 kilogram, 2 kilogram and 4 kilogram. Here 2 kilogram is kept 20 newtons. Normal reaction R1 equal opposite normal reaction here. Here it's going to be 40 Newton. Here normal reaction R2. Here there's a force. Two boxes, 2 kg, 4 kg are kept on a horizontal smooth surface. Here horizontal smooth surface. Now here there's going to be a dynamic friction or a static friction. There you go, it's marked. Find the maximum horizontal force that can be applied on 4 kg such that 2 kg mass does not slip. Maximum force. Maximum force here will occur. Maximum force will occur when both of them are moving together. Limiting friction. Limiting friction. Maximum horizontal force. So when limiting friction occurs, this is part A. When limiting friction force occurs, when limiting friction force occurs, when limiting friction force occurs, maximum force here means maximum acceleration. Therefore, maximum acceleration will occur. Maximum acceleration will occur. Okay. Let's work it out. Apply F equal ma on 2 kg mass. Limiting friction Fs, mass into acceleration. Look at the board carefully. Limiting friction is mu s times normal reaction R1. There you go. Mu s is already given. Mu s is 0.3. R1 is 20. 2 times A. Acceleration is 3 ms minus 2. There you go. Acceleration found. Acceleration found 3 ms minus 2. If acceleration is found, what else do you need? Maximum force. Here you are applying for Roman 1 still. F equal ma in the forward direction, apply for 4 kg. F naught minus static friction, mass is 4 times, same acceleration 3. F naught minus static friction here, this is going to be how much? 0.3 times 20. Yeah, multiplied 0.3 times 20, 12. F naught minus 6 equal 12. F naught equals how much? 18 Newton. F naught equals 18 Newton. Count. So remember, maximum possible force for them not to slip. Here also they are saying no slip condition. No slip condition means they are moving together. Simple. Don't forget that. Find the acceleration for each mass when F naught is double. When F naught is double, what happens is they won't go together. Dynamic friction will act. Right there. Right there. When F naught is double, when F naught is double, 36. When F naught is double, dynamic friction will act between A and B. Dynamic friction will act between A and B. Dynamic friction will act between A and B. Okay. So they're asking to apply separately. F equal ma. Anyway, I will apply on 2 kg. Dynamic friction is mass into acceleration. Mass is 2 kilogram. Acceleration A. Mu k times normal reaction mass into acceleration. Mu k is equal to 0.2. Normal reaction 22 times A. Acceleration equals 2 ms minus 2. So acceleration of 2 kilogram object, that means acceleration of M1 object is 2 ms minus 2. Now apply F equal ma on 4 kilogram object. Apply F equal ma on 4 kilogram object. F naught minus dynamic friction, mass into acceleration. Acceleration will be different. Mass of M2. F naught is given 36. Mu k times normal reaction equal 4 times acceleration of M2, right? 36. Mu k is 0.2. Normal reaction, how much? 20. 4 times mass into acceleration. That means you are applying for this condition. But here you have a dynamic friction. Here you have dynamic friction. Best is you can draw and show that. It will be useful. So here you have normal reaction R1 equal opposite normal reaction R1. Here 20 newtons, here 40 newtons. Here normal reaction R2. Here I am applying 36 Newton. The moment you apply 36 Newton, here there will be kinetic friction. Equal opposite kinetic friction. This will travel with a different acceleration. This will travel with a different acceleration. There you go. Acceleration of M2. Do the substitution. 36 minus 4 equal 4 times mass into M2. 32 is equal to 4 times acceleration M2. Acceleration M2 is equal to 8 ms minus 2. Acceleration can be found. Acceleration can be found. So this is Roman 2. This is Roman 2. So if the forces are doubled, guaranteed, here you have a dynamic friction. Okay. Find the acceleration of such manner F naught is half. Now F naught is 18 here. No? When F naught is 18 here, maximum limiting friction. When F naught is doubled, dynamic friction. If F naught is halved, then was a static friction but not limiting friction. F naught 18, maximum static friction. F naught doubled, dynamic friction. F naught is half means yes, it's static. F naught 18 static means F naught half was static to 9 was static. But it's not limiting friction, it's just static friction. Right there. When F naught is half, it will travel together. It will travel together with mass M1. With mass M1. And there will be a static friction. As there will be a static friction, Fs dash. Static friction. Acting. There will be a static friction acting. So here also Roman 3. No slip. Huh? No slip means they will move together. If moving together, what will you do? Apply F equal ma completely for the system. If you apply completely for the system here, static will cancel off. Here total mass is 6 times acceleration. Acceleration is 3 divided by 2. Answer is 1.5 ms minus 2. Then what? Then you apply F equal ma. Here at 2 kg. Static friction is mass into acceleration. Static friction, we don't know. Mass into 1.5. That is 3 newtons. Okay. Static friction is 3 newtons less than limiting. Okay. What else? Find the acceleration. Find the friction force. Done. Roman 3 done. Right. Roman 3 done. Part D. Part D. 2 masses 5 kg and 10 kg. 5 kg and 10 kg. are kept on a smooth horizontal surface. Kept on a smooth horizontal surface. Okay. Now here you can see connected to a mass passing over a pulley, another mass is there. Another mass is there. String is connected to M2, 50 newtons, normal reaction, equal opposite normal reaction, 10 kg, 100 newtons, normal reaction R2, normal reaction R2. Okay, normal reaction R2. Now, here you have M3. Here M3 is connected. M3G. Here tension, here also tension, here also tension. Light inextensible string. Light inextensible string. Right. What are they asking you? System is released from rest. Coefficient of static friction. That means here in between the surface here, coefficient of static friction and dynamic friction are given. Find the maximum acceleration of M1. Maximum acceleration. Now your experience. Maximum acceleration occurs when there is limiting friction here. When there is limiting friction there. All right, Pilu. Maximum acceleration for M1 occurs. Maximum acceleration for M1 occurs when there is limiting friction acting between M1 and M2. When there is limiting friction acting between M1 and M2. When there is limiting friction acting between M1 and M2. Let's find limiting friction, mu s into normal reaction R1. Let me apply carefully. Here part or Roman 1. Roman 1. F equal ma in the forward direction acting on 5 kg mass. Limiting friction is mass into acceleration A. Limiting friction is mu s into normal reaction 5 times A. Mu s is already given 0.6. Normal reaction is given 50, 5 times A. Acceleration equals 6 ms minus 2. There you go. Maximum possible acceleration is 6 ms minus 2. So these are from the earlier question, the experience you have, you apply it here. What else? What is the maximum acceleration that M2 can have such that M1 does not slip on M2? Maximum acceleration that M2 has, that no slip takes place. So here maximum acceleration is here. Even in the earlier problem here 1.5 when it's static. When it's dynamic, here, when it's dynamic, acceleration is how much? Acceleration of M2 is maximum. M1 is going to be minimum 2. If you look at the values, that's because F0 is increasing. Right. What are they saying? Maximum acceleration that M2 can have such that M1 does not slip. Condition is given. Now here if you put dynamic friction, it's slipping. Two different. Here you can't apply. So here Roman 2 was the answer is same. Maximum acceleration will be 6 for no slip. For no slip. Okay. What's the maximum value for M3 sun have such that M1 does not slip on M2? M1 does not slip on M2 maximum acceleration. So if you work the problem out, you can work the problem out here. So here tension minus 30. Tension minus limiting. So here if you substitute F equal ma forward on M2. Tension minus limiting friction, mass into acceleration. Mass is 10 times, acceleration is 6. Here it's going to be mu s times normal reaction, 60. Mu s is 0.6, normal reaction is 50. 60. Here 30, tension is 90. If tension is 90, apply F equal ma downwards on M3. M3G minus tension equal M3 times acceleration. Same acceleration 6. M3 times 10 minus tension is 90. M3 times 6 in this side. 4M3 equals 90. M3 equals to 5 kilogram. 22.5 kg. 22.5 kg. Okay. So there you go. Whenever they say no slip, that means both the objects are moving together. Don't forget. Okay. Both the objects are moving together. Right. So today we'll discuss question 3 and stop. Then next week we can do question 4 and 5. Right. Question 3. Yeah, look. Question number 3. State the law of conservation of linear momentum. What is linear momentum? Right there. This should be the inverse. When there is no external force acting on the system, when there is no external force acting on the system, the total linear momentum of the system is conserved. The total linear momentum of the system is conserved. Total linear momentum of the system is conserved. Right. Roman 2 part A, B. Roman 1 is done. Roman 2. Two astronauts are at rest in zero gravity and they push on each other. Mark the forces. So astronauts are like this. They're pushing on each other. So if I mark the forces on them, this is pushing. A is pushing. B is pushing A. Those are the forces. What are the zero gravity? So no wait. What's the initial momentum of the system? So initial momentum is 0. But don't just put 0. Kg ms minus 1 in the direction. What's the total momentum of the system when they are moving away from each other? Total initial momentum equal total final momentum. 0 kg ms minus 1. Same direction. Sorry. Same direction. Part D. Mass of A and B is 100 kilogram and 50 kilogram. What is the distance moved by B when A has moved 3 meters? So when they push on each other, earlier they were very close. Now they are pushing on each other. A has gone here. Here you go. A is somewhere here, B is somewhere there. Let's say starting position is here. Distance moved by B when A has moved 3 meters from the initial position. Now, whenever you have a problem like this, don't panic. Simple. Actually, if it's MCQ advanced, you can write in terms of displacement. Okay? In terms of displacement, mass into displacement of A, mass of B to displacement of B. They're asking the displacement of B. Yeah. A is 100 kilograms. B is 50 kilograms. There you go. Right. Now carefully work. Total initial linear momentum equals total final linear momentum. You have to explain this in words at least once. Total initial linear momentum of the system equals total final linear momentum of the system. Initial linear momentum of the system is 0. Final linear momentum is also 0. 100 is going backwards. Velocity of A with respect to Earth. B is going forward. Velocity of B with respect to Earth. Velocity of A with respect to Earth in that direction. 50 velocity of B with respect to Earth in the forward direction. Simple. Now bring both vectors in the same direction. I can solve it here. 0, 100 velocity of A with respect to Earth minus 50 velocity of B with respect to Earth. Then I change the direction. Simplify it. 100 velocity of A with respect to Earth equal 50 velocity of B with respect to Earth. Velocity of A with respect to Earth means displacement divided by time. B with respect to Earth means displacement divided by time. Simplify this. Tt cancel off. 300 divided by 50. XB is 6 meters. 300 divided by 650 means 6 meters. There you go. Part D done. Part D done. Roman number 3. Roman number 3. Roman number 3. Now A and B at rest on ice, push on each other as shown. Now on ice. Some of you all have drawn the same diagram. Why are you drawing the same diagram? You're on Earth. Mark all the forces means yes. Push is there. Same line. That is how they look. Same line. Don't forget the weights. 1000 Newton. 500 Newtons. What's the distance moved when B has moved 2 meters? So here B and A has gone somewhere here. B has gone somewhere here. What's the distance moved by A when B has moved 2 meters? Right. So don't forget velocity of A with respect to Earth. Velocity of B with respect to Earth. Marks are given. Marks are given. Total initial linear momentum of the system equals total final linear momentum of the system. Okay. Total initial linear momentum is 0. Total final linear momentum. If you work the problem out carefully, same two people, 100 velocity of A with respect to Earth backwards, 50 velocity of B with respect to Earth forwards. Finished. Bring all vectors in the same direction, A comma E backwards, minus 50 B comma E. Simplify it, 100 B A comma E, 50 B comma E. A comma E, distance of A, same time. B comma E, distance over same time. Distance traveled by A will be 1 meters done. 1 meters done. Part B. Part B. Okay. Part B. Two children are standing at two ends of a 100-meter long boat. Boat length is given 100 meters. Boat length is given 100 meters. What else? Mass of the boat with the children on it 100 kg. There's a child here with a ball. There's a child here with a ball. Empty, waiting to catch. Right. Okay. Question. Right now. One child throws the ball. One child throws a ball of mass 10 kg towards the other child. With a horizontal velocity 20 relative to the ground. The velocity of the ball is given. What will be the velocity of the boat relative to the ground? So when I throw the ball that way, boat is going forward. Boat is going forward. This child will catch it. Right. Have a look. displacement of the ball plus displacement of the boat is going to be total length. This is velocity of boat with respect to Earth. Ball is traveling. Velocity of ball with respect to Earth, how much? 10 meters per second. 10 meters per second, right. Let's do this. Roman 1. Total initial linear momentum of the system equals total final linear momentum of the system. Now what? Total initial linear momentum, you can say 0. Total final linear momentum, look at this carefully. Ball 10 kilogram, velocity of ball with respect to Earth going forward. 100 kilogram, boat and children. Velocity of boat with respect to Earth going where? Backwards. Velocity of boat with respect to Earth going backwards. Simplify it, bring all vectors in the same direction. Ball with respect to Earth, change the direction. 100 boat with respect to Earth. Now we can solve this. Ball with respect to Earth equals 100 boat with respect to Earth. What are they asking? So ball with respect to Earth is 20. Boat with respect to Earth you can find. Velocity of boat with respect to Earth 200 divided by 100 is 2 meters per second. 2 meters per second. That. Find the time taken by the other child to catch the ball. So now you must be very careful. Displacement of the ball. This is displacement of the boat. Displacement of the boat and the ball is 100 meters. Right. Time taken. So we can actually simplify this quickly. We can do it here. And it's like this. 10 velocity of ball with respect to Earth. 10 velocity of ball with respect to Earth. 100 velocity of boat with respect to Earth. Displacement of ball, same time. Displacement of boat, same time. Displacement of ball is 10 times the displacement of the boat. Solve this carefully. How is it? Displacement of ball plus displacement of boat, 100 meters. What are they wanting? Time taken to catch the ball. 10 times displacement of boat plus displacement of boat is 100. Displacement of boat is equal to 100 divided by 11 meters. Displacement of ball is 10 times that. 1000 divided by 11 meters. 1000 divided by 11 meters. Now you can find the time taken. How will you find the time taken? Time taken is displacement of ball with respect to Earth divided by velocity of ball with respect to Earth. 1000 divided by 11 divided by velocity of ball with respect to Earth 20. Simplify it. 50 over 11. No? 50 over 11. So if you do the simplification, 4 point, for 60 you have 5, 50 you have 50 you have 4. Again 5, reoccurring. Time taken found. So Roman 2 found. Roman 3. What is the velocity of the boat after the child catches the ball? So when the child catches the ball, after the child catches the ball, not just before the child catches, after the child catches the ball. After the child catches the ball against what? Again what? Same as earlier, no? Momentum becomes zero, velocity will become what? Zero. He's at rest. He throws the ball, boat goes. The other fellow catches it, stops. Then momentum zero. Then the boat can't move. After catching the ball, 0 meters per second speed of boat. Roman 4. Second child catches the ball and throws the ball at the same speed horizontal. Find the displacement of the first child from the initial position when he catches. Now what happens? Look what happens. This ball will throw there, boat goes forward. This ball is throwing here, boat will come backwards. Same position. So displacement of the child is going to be what? 0. Right there. When the second child throws the ball forward, the boat will travel backwards. The boat will travel backwards the same distance. Understood, no? When I throw this, it goes forward. When I throw there, it will come backwards. Therefore, the displacement of the first child will be 0. Therefore, displacement of the first child will be 0. Right, Roman number 5. So it goes forward a distance 100 over 11. It will come backwards also a distance 100 over 11. Distance traveled by the boat. 0 meter displacement. Distance traveled by the boat. That's going to be 100 divided by 11 forward, 100 divided by 11 backwards, 200 divided by 11. 200 divided by 11 means 1 is there. For 90 you have 8, 88. For 20 again 1, 8 meters. 18.18 meters. Right. It's a very simple but important question. Interestingly simple. Clear? Very few things to do. Part C. Explain how a rocket obtains thrust required to move upwards. You can explain that. How does it happen? It will burn hot gases and emit hot gases. So when the gases are emitted backwards, the rocket is pushed where? Forwards. So rocket is pushing the gas backwards. Gas is pushing the rocket where? Forwards. Right there. When hot gases are burned, see Roman 1. When hot gases are burned, the rocket will push the hot gas downwards. While the gas will push the rocket in the upward direction. Done, na? Roman 2. If the rate of combustion is capital M, exit velocity U, show that the thrust force on the rocket is mu. So thrust is equal to mu. Mathematically, there is no need to prove it, but if you want, you can show this in dimensions. Thrust is a force mLT minus 2. Here, rate in which it's burned mt minus 1 into LT minus 1. Simplify it, mLT minus 2. So thrust is equal to a force. So mu will give a force. Okay. Roman 3. If the rate of combustion is constant, the thrust force on the rocket is constant. Explain the variation of the exit velocity of the exhaust gas with time. What are they saying? Thrust is equal to mu in Roman 3. What are they saying? They are telling you this is constant. That is constant. Thrust force is constant. What can you say? Therefore, u is also constant. Exit velocity is also constant. Roman 4. When the rocket is just about to take off, rocket is just about to take off. Huh? Rocket is just about to take off. Mass of the rocket is 10 to the power 5 Newton. Thrust is there. Find the initial acceleration. Find the initial acceleration. So they are giving you thrust minus mg mass into acceleration. Thrust equals rate in which fuel is burned, mu, minus 10 to the power 5, 10 to the power 4 times a. 2 10 to the power 3 multiplied by 500, 10 to the power 5, 10 to the power 4a. 10, 10 to the power 5 minus 10 to the power 5, 10 to the power 4 times a. 10 to the power 4 cancel off. 100 minus 10 equal a. Acceleration is 90 ms minus 2 acceleration. 90 ms minus 2 acceleration. Assuming the acceleration is constant, they're asking, assuming the acceleration is constant, they're asking velocity of the rocket v equal u plus at, starting from rest 90, 10 seconds later, 900 meters per second. Velocity of the rocket 900 meters per second. Okay. Now Roman 5, with the mass of the rocket in 20th second, the fuel is burned. Mass remaining. Mass burned. I will do that to mass burned. 2 10 to the power 3 multiplied by 20 seconds. 40 10 to the power 3. That's going to be 0.4 10 to the power 5 kilogram. Okay. So if you simplify it, 4 10 to the power 4 kilogram. But mass of rocket is 10 to the power 4. This means fuel must burn out earlier than 20 seconds. Total mass of the rocket only is given. Mass of the rocket total with the fuel 10 to the power 4. After 20 seconds, the burnt mass is 4 10 to the power 4, more than the actual mass of the rocket. That means before 20 seconds, it's fully burned. Part B, find the acceleration of the rocket at the instant when if the thrust force is equal to the initial value. Part B, find the acceleration of the rocket where the thrust force is equal to the initial value. Now, actually, because this part A part is done, part B, there's a typing error there. it should be find the acceleration of the rocket at the instant when the thrust force is equal to the weight. Since it's not given, I gave all for that. I gave marks for that. But anyways, if I do it for y'all, correct it there. Thrust force equals weight. So if I apply F equal ma upwards, thrust is just equal to weight. Thrust is equal to weight means initial acceleration how much? 0. Thrust is equal to weight means initial acceleration 0. So that correction there, right? The thrust is just equal to the weight. Okay? Thrust is just equal to the weight. The initial acceleration will be 0. Vertical firing. Okay, right. So we have discussed 3 essay questions. So next helpline we will discuss question number 4 and question number 5, and then complete the discussion. Look at these 3, learn from it, correct your mistakes, and then we move forward. Okay, take care. See you all next week.